Hello, Mr. Patterson here, and in this video we're going to be going over the representing molecules review. Please make sure that you follow along with the thought process behind each one of these answers. All right, the first three problems here ask for a numeric response. So you're going to have to figure out how many electrons or bonds are involved in each of these molecules. All right, so number one, how many unshared pairs of electrons does the nitrogen atom in ammonia possess? So unshared pairs, well, that's another word for lone pairs. Okay, so we need to look at ammonia, which is NH3. So let's draw it. All right, so NH3. Let's see, total number of electrons. Nitrogen gives us 5 plus 1 from each hydrogen. That's a total of 8 valence electrons. Nitrogen goes in the center because hydrogen always goes on the outside due to it only being able to have 2 electrons around it in its outer energy level. So we've attached the nitrogen to the hydrogens. I've used 2, 4, 6 electrons, so the lone pair has to go on nitrogen. So we have 1 lone pair. So the answer for that first one is 1. All right, so let's take a look at number 2. How many covalent bonds are in a covalently bonded molecule containing 1 phosphorus and 3 chlorine atoms? So let's do the same thing as we did before. Let's come on over here and draw this. 1 phosphorus and 3 chlorines, so PCl3. Let's look at how many electrons that we're dealing with. Phosphorus, that's going to be 5, plus chlorine. We have 3 of those with 7 valence electrons each. That's a total of 26 valence electrons that we have to work with. Phosphorus goes in the center because it's the lowest electronegativity. Chlorine's on the outside. So we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6. Okay, there's my correct Lewis structure for phosphorus trichloride. We're asked how many covalent bonds there are, and we've got 3 of those total. So 1, 2, 3. Now it wouldn't be any different if it was a double bond or a triple bond in here. A bond is a bond. All right, the double, triple, or double and triple bonds just tell us we're sharing more pairs of electrons. All right, so the answer here is 3 covalent bonds. Next one, number 3. How many unshared pairs of electrons are in a molecule of hydrogen iodide? All right, so come back over here. We're going to do hydrogen iodide, Hi. All right, 1 electron from hydrogen. Iodine has 7, so that's a total of 8 electrons. We don't have to worry about which atom is in the center because there are only 2 atoms to deal with. So I've bonded them together and put the rest of the electrons around the iodine. So I have 2, 4, 6, 8 electrons used up. My Lewis structure is good. And we're asked about how many pairs of lone pairs or pairs of unshared electrons there are. So we've got 1, 2, 3. The answer for that one is 3. Okay, now down to the completion. A molecule or part of a molecule that contains both positively and negatively charged regions is called a, you can put a couple different answers in here. You can have polar molecule. All right, that would be acceptable. All right, or you could have a, what we call a dipole. So that's just a molecule or a bond that has that positive and negative region. All right, next one, number 5. If the difference in electronegativity values between 2 elements is 0.1, they will most likely form a non-polar covalent bond. There's not a big enough difference in electronegativity to shift the electrons in the bond from one atom to the next. Number 6, if the difference in electronegativity values between 2 elements is 1.3, they will most likely form a polar Now we've got a big enough electronegativity difference that the electrons are shifted from one element to the next. All right. Number 7, in the compound HCl, or hydrogen monochloride, the atom of the element blank carries a partial positive charge. Okay, let's take a moment and think about this one. All right, so hydrogen chloride, HCl, that's going to look like this. Okay, what we are concerned with is which way electrons are shifted in that bond. All right, so this bond is what we're concerned with. Chlorine is more electronegative than hydrogen, so the electrons are going to be shifted in the bond more towards the chlorine. So we're going to have a dipole moment that's pointing towards the chlorine. Now, let me represent this a little differently. Let's put the hydrogen here, and let's put the chlorine atom here. The electrons are going to spend more time around the chlorine here. So they get shifted towards the chlorine. This end will have a partial negative charge. This end will have a partial positive charge because the electrons are shifting towards the chlorine. So to answer the question, the hydrogen atom will have a partial positive charge. The electrons are shifted from it towards the chlorine. Number 8, non-bonding pair of electrons in the valence shell of an atom is called, okay, it's non-bonding. It's not taking part in the bonding, so we call those lone pairs. They're not attached to anything. They're not attaching two atoms together. Covalent bond, number 9, a covalent bond in which two atoms share one pair of electrons is called a, you can put single bond or single covalent bond. Number 10, in the Lewis structure of a molecule, a blank bond is correctly represented by a long dash. So if it's one long dash, we're going to call that a single, and that would be covalent. Single covalent bond. All the bonds in Lewis structures are going to be covalent, but the important part here is a dashed line, a single dashed line is a single bond. Number 11, a covalent bond in which two atoms share two pair of electrons. That's going to be a double bond. Covalent bond in which two atoms share three pair of electrons is called a triple bond. Okay, moving along to the next page. So you're going to match these up. You're going to match the molecular shape with the compound. All right, so what you're going to have to do for each one of these is draw the Lewis structure and think about the three-dimensional shape that is associated with it, and then pick the correct model. Number 13, dihydrogen monoxide. Well, dihydrogen monoxide is water. The Lewis structure for water is going to be like this. I have 1, 2, 3, 4 areas of electron concentration around oxygen. Those are best spread out in a tetrahedral pattern, but notice you have two lone pairs. So you can build the tetrahedral structure. All right, let's see if I can draw that here. So I've got oxygen, and let's do a lone pair here, and a lone pair here. So what's that going to look like in 3 dimensions? It's going to look like this right here. All right, so that's going to be C. The next one, nitrogen trihydride Nh3. That's ammonia. The Lewis structure is like this. So once again, 4 areas of electron concentration around the nitrogen. We're going to start with a tetrahedron, but right here, we have a lone pair, so there's not going to be anything bonded there. And that's going to end up looking like this shape right here. Now remember, those electrons, whether they're lone pairs or bonding pairs, are trying to get far away from each other. So you got to know the best shape to get those electrons as far apart as possible. Number 14 is going to be E. Number 15, carbon dioxide. All right, that is CO2. Lewis structure is going to look like this. So areas of electron concentration, this one's a little different. We have 1, 2 around the carbon. The best way to get them spread out is for them to be 180 degrees from each other on the bond angle. And that's going to give us a linear shape, and that would be shape B here. Carbon monoxide, CO. All right. Lewis structure is going to look like this. Okay, so that is going to look like A. Carbon tetrafluoride, CF4. Carbon in the center, fluorines on the outside. Now I'm drawing in a bunch of lone pairs around the fluorines, but notice they're not around that central atom, not around the carbon, so it's not going to influence the shape. So we have 4 areas of electron concentration, 1, 2, 3, 4 around that central carbon. That's going to give rise to a tetrahedral pattern. It's going to look like D. All right, so number 17 is D. Number 18 here, we have CH3Cl. Okay, that's chloromethane. Don't worry about the naming scheme for that. Just know how to draw the Lewis structure. Carbon in the center, hydrogens on 3 sides with the chlorine on 1 side. All right, so we've got 4 areas of electron concentration. It's going to look like D once again, that tetrahedral pattern. Okay, let's move on. For 19, you want to draw the Lewis structure for the oxalate ion, C2O4, but notice it's an ion, it's got a charge on there. All right, so let's go over to the side here and let's draw that. C2O4 with a 2- charge, that's a polyatomic ion. So I have 2 carbons, each contributing 4 valence electrons, plus 4 oxygens, each contributing 6 electrons, plus 2 more electrons because it has a negative charge. I believe that's a total of 30. Let's see. We have 8 here plus 24 plus 2. I believe that is 34 electrons that we have to account for. All right. So least electronegative goes in the center. So we have carbon bonded to carbon. Our oxygens are going to go on the outside here. We're going to start with single bonds. You're going to end up with a structure that looks like this. All right. Now, let's see. I've used all of my electrons. I've satisfied the octet rule all the way around. Okay. One thing I do want to point out, notice how these double bonds are opposing each other. They're not on the same side of the molecule. I would not take off for that. Okay, I would not do that. But if we think back to how electrons interact, they want to be as far apart from each other as possible. So the double bonds would be on opposite sides of the molecule. That would give us the most accurate representation of that ion in this case, or a molecule if it didn't have a charge. Number 20, draw a Lewis structure for the ammonium ion, NH4+. So same idea here. All right, so we have NH4 with a positive charge. So you have 1 nitrogen contributing 5 electrons. And you have 4 hydrogens contributing 1 electron apiece. But since we have this charge here, we're going to have to subtract an electron. So we're going to subtract an electron there. So that should give us a total of 8 electrons to work with. Nitrogen in the center, hydrogen's all the way around here. Okay, there's our Lewis structure for that one. All right, so it's going to look like this. Hydrogen here, hydrogen here, hydrogen here, hydrogen here. All right, now down to the essays here. 21, explain what is meant by Vesper Theory. Give an example of how Vesper Theory can be applied to predict the shape of a molecule. So, I'm going to give you these, and you can write them down. But I'm gonna make some notes here. All right. So for 21, just a couple quick notes. What is meant by Vesper Theory? That is valence shell electron pair repulsion. All right. What that means is electrons try to get as far away from each other as possible. Okay. So electrons repel, and they spread out as far as possible. All right. So give an example of how Vesper Theory can be applied to predict the shape of a molecule. So basically, the repulsion determines the shape of the molecule. Okay, and there were 5 basic shapes that you needed to know. You might want to go back and review those. Okay, now 22. Take a look at 22 here. Let's change colors here. Let's do 22 in red. Okay, 22. Explain what a polar molecule is and provide an example. All right, so a polar molecule. This is a molecule with positive and negative ends. All right. So an example. I'm going to give you the most common one, H2O. Now, don't just give the example. Explain it. All right. So that's what I'm going to do here. So we have oxygen bonded to hydrogen. And there's some lone pairs here. Now, the dipole moment in each bond. Oxygen is more electronegative. The dipole moment in each bond is towards the oxygen. Electrons in those bonds get shifted towards the oxygen. So this end of the molecule becomes slightly negative, and this end of the molecule becomes slightly positive. Okay, so when you're looking for polar molecules, make sure that your molecule has polar bonds in them, which we have here. The oxygen is pulling the electrons in the bond towards it, stronger than hydrogen is. So that's the polar bonds. And you're looking for an asymmetrical shape, which is what we have here. All right. So there is the representing molecules review.